Hello, this is Ungsap Kim, and this is an online class for the national holiday. In last class we have talked about something about computer algorithm for the addition and multiplication. And in addition, we give some basic simple algorithm like this. Align two numbers to the right and perform a single right to left pass. It's an algorithm. Okay, so maybe we guarantee that this is correct one because we have used this method so far from your very young age, and we know that is correct algorithm. Then next step is to analyzing the time complexity. That is execution time. Okay, so execution time. Okay, that is the execution time is in computer algorithm. We say that time complex. Okay, because in execution time we don't measure the real execution time. Just we count each statement for solving some problem, and that is we say that that is time complex. Okay, so anyway, the time complex is big over n. Okay, when n is the number of digits. The number of digit means the count of the total 0 or 1 digit. Okay, for all input numbers. Okay, so number of digit means when the number is 11000, then the number of digit is 5. Okay, when the number is, then the number of digit 6. Okay, okay, so that is in terms of number of digits. This is a big over n because you have to add all the digits. Okay, from the both number, including carry. Okay, so that will take big over n time for the addition, and we have to read all the digit, the given digit. Okay, before we add something. So total action time is will be big over n because reading digit takes big over n and adding digit will be big over n. So total big over n plus big over n is big over n. Okay, so n is the number of digits of all the input number. Okay, so how about the multiplication? In this case, the multiplication is not that hard. Just in this case, there's two number, two uh, both are written in binary number. Okay, so in this case here the upper number and lower number, and upper number is some number composed of one or zero. Okay, and here also composed of one or zero. Okay, so in case one, then this number will be written directly. Okay, here directly of number written indirectly here. Okay, and this is young 0. Okay, then in this case okay, this number will be 0. Okay, except that in this case, okay, written directly here. Okay, if the number is 1, then this number is written directly here, and this number is 1, this number will be written directly here, but their location should be aligned to the number, okay, like this, okay. So, and once you have all the number, then add all together, then finally you get the resulting number like here, okay. That is how to add two number in binary digit, okay. So this method is very useful for calculating two number, multiplying two number in computer CPU, and currently computer CPU is using this kind of method for multiplying two number, okay. And especially the computer CPU is using binary number, not decimal number. So in computer CPU, when CPU need to multiply two number, then maybe this CPU have two number in terms of binary digit, okay. So when they computer CPU need to multiply two number, then they are using this kind of method just to write down directly when some number is 1 and there's some alignment here, and there's no number writing here when this guy is 0. So finally this is a way to multiply two number, okay. And so in this case, because this method is very useful for computer CPU, and this is the popular method for multiplying two digits in terms of binary numbers, so that must be correct, okay. So finally you have two number and you need to calculate the execution time. Then in this case, okay, so there is some writing down something takes the big O of n time, and there is some number of rows. Number of rows is big O of n, so n by m, so total execution time will be n square, okay. So that means that is this guy, okay, this guy is of n, okay, and this guy will be n, okay. So this guy, the length of digit is big O of n, and the number of columns is number of rows big O of n. So total action time will be big O of n square. Okay, that is the time complex for the multiplication. So next step is we have to think about is it okay, and time, okay. So that's the next step. So at this time, okay, big over n square is okay, fine, but maybe we have to think about is there any faster way to calculate the multiplication? So we have to okay. Okay, so maybe we can consider next alternative method to multiplying two numbers. Okay, so this is alternative method. The basic idea is simple. You have two number, okay, and to multiply each number, then rather than calculating some kind of multiplication method, just you have 아이고. Okay. Okay. You have double. No, no, no. Get half and get double. Okay. So one side you have two number, you have double volume number, and you have half volume number. Then that will be is the balanced, and you will get the same value. Okay. So you get half, 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 double, double, double. Finally, you will reach some number like one. Okay, so you have the other in other side you will have some kind of the bigger number because this is get double, half. Okay, so finally you have this kind of number. Okay, but in this case you have to think about this is odd number. Okay, if you get half, get double, and you lose something. Okay, because this is not even number. Okay, so in this case you have store some value for compensate some loss. Okay, for half and double. Okay, so in this case get half and double, no problem. Okay, this is even number, so get half double, it's no problem. But other case is get half, get double, you will lose some values. Okay, so you to make up this loss, so you just store some value like here. Okay, and then finally you add up all together 16, so 13, 26, 104 all together. You finally have your answer like here. And for this method, you don't have to memorize some method of some multiplication like 7 times 9 or 6 times 4. You don't have to memorize the actual value of 6 times 4 or 7 times 9. You just double and get half. That is simple. And you memorize some values when you have odd number. Okay, and you need to double down. Okay, for this number. Okay, so this is this method. So it will make correct answer. Okay, you get half, you get double. Okay, so finally you did this number is same. Okay, so when you have this kind of algorithm, this algorithm can be written like this, recursively like this: x times y equal 2 times x times y half here. Okay, and but in this case y is even, no problem. Okay, this x number gets double and y number get half, no problem, it's the same. But when y is odd, then this this equation have some loss. Okay, so you have to make up the loss. So when I is odd, then you have this kind of value. Okay, so once you have this kind of recursive recursion, then you can write down pseudocode for multiplication with recursion. Okay, like here. Okay, so x times y is 2 times x times y by 2. Okay, when y is even. Okay, so y is even, then you have y times y by 2, and you need to multiply the number once. Okay, but in case y is odd, then you have to add x. Okay, so you have to add x. Okay, just simple. Multiply x times y. This is multiplying. This is multiplying. And first, you have to multiplying this number first, and that is written in here. Okay, multiplying and multiplying. Okay, so once you have this number, then you have to double the result of this calculation. Okay, you have to double here, and but when y is even, then you double the number simply. And y is odd after you get some double number and you have to add x again, okay? So that is, this algorithm can be recursively written in this form, okay? So now, in this case, okay, you can claim that, okay, this is correct algorithm because this is from here and this is from here, okay? And this algorithm is popular way and this correct way and used in some country, okay? So now next time is we have to calculate the time complexity. Okay, so in this case, maybe we can write down in this form here. T n equal what? Okay. Initially, this guy is a t and get half. Okay. So t n minus 1. Okay. Plus. Okay, Tn equal, okay, I'm sorry, I will write down again, okay. So this guy is Tn, and okay, this guy is, our goal is to calculate the Tn. In this case, okay, let's think about this case. Okay, this guy takes big over 1, okay. And how about this guy? How about this guy? This guy takes Tn. Maybe it's the same, Tn, but only different side is here, y by 2. So maybe this guy, no, this should be t minus 1, okay? Because the input is 2-digit n-digit integer, okay? So in this case, okay, let me think about y equal, when y equal 0, 0, 0, okay? Okay, then y by 2 will be here, okay? When y equal, then y by 2 is 0, okay? Okay, so that is clear. So y's number bit is 5, and 4. y by 2's number of bit equals 3, okay? Okay, y's number of bits equals 5, y by 2's number of bits equals 4, okay? Okay, so that's it. That is, so that's why this is Tn and this is Tn minus 1, okay? Because the input is a 2n-digit n-bit integer, input to n-bit integer, okay? X is n-bit, y is n-bit, and if you divide certain number by 2, then the number of bit get lessened by 1, okay? Can decrease by 1. So here is the example. When y equal 1, 0, 0, 0, then y by 2 is 1, 0, 0, okay? When y equal 1, 1, 1, 0, 0, y by 2 is 1, 1, 1, 0. So y's total number of bit is 5 in this case, and y by 2's number of bit is 4, okay? So this number of bit is decreased by 1, so that's why this is a Tn minus 1, okay? And then how about this guy? Okay, higher, the y is even, okay? How about this guy? And this is big over 1, okay? And how about this guy? 2 times y, okay? So this guy, okay, this is big over 1, okay? And this is addition, so this is big over n, okay? Because addition add, this is addition of 2 n bit digit numbers, okay? Now, so here y it is n bit, okay? 2 digit is done by shift operation, okay? And shift operation is taken in big of 1, okay? Okay, so like this, okay? So then, what is shift operation? Okay, I have to explain something about the shift operation. Shift operation, it's a left shift operation. There are 2 types of shift operation. One is left and the other one is right shift operation. Okay, I'm missing somewhere here. So left shift operation is like this, okay? If you have number 100, then that will become 10000. Just one number is shifting, okay? So in other words, you can write down like this, okay? And right shift operation is like this. If you have number 0100 becomes by right shift operation 0010, okay? So that is the number 1 is shifted one bit left or right, okay? Shift 1 bit, okay? So typically shift operation is done by big O over 1 time. In typical computer operation. Okay, here is the one. Okay. Okay, here. Okay, shift operation. Okay, so 2 times G. Okay, doubling of a certain number can be done with shift operation. Typically, it's just not shift. This is done by left shift operation. Okay, left shift operation is just when you have some binary digit number, just kind of rotating that number. So from here, make there. Okay. So from here, in right shift operation, from here, make it like this, okay? So maybe we can give another example like this, okay? 00. So left shift operation 011000, okay? So that is left shift operation, okay? And there's shift 2 type of shift operation, right and left shift operation. So this can be done by shift operation, okay? So total action time will be, if we add all together, then this equation can be written in like this, okay? T n equal T n minus 1 plus big O of n, okay? So by using recurrence relation, and you can calculate the result will be total action time will be big over n square, okay? So anyway, this multiplication takes big over n square. And previous example of multiplying two binary digits takes big over n square, and this method takes big over n square. So same, okay? So alternative method looks like faster, but it's the same in terms of algorithmic time complexities. So no big difference between previous and this method. So at this stage, we should say that okay, that is fine. N square is good fit. Okay, there's no alternative method. Okay, so and next step is division. Okay, it's division has two n-bit number, and there is some quotient and remainder of x divided by 2. That is division, okay? And that is division algorithm can be written like this, okay? So basic idea is like this, like here. So you have device number like QR, and if you get doubled and doubled, okay, and then finally you have, okay, the result, okay. Assume that this division method is correct one. The next step is calculating action time of this method, this algorithm, okay. Likewise in the previous slide, okay, about multiplication, we can compute this division method using recurrence relation like this, okay, n minus 1, okay. And look at this example. There's nothing. This is a shift. This can be done with the shift operation. There is addition, and there is the subtraction here. So there's except this guy, there's nothing bigger than big O over n. Okay, so this can be written like a big O over n. Okay, so this once your recurrence relation is written like this, the total action time will be n square. Okay, so in this case, look at this. This guy takes, okay, this big O over 1. Okay, this guy takes Tn minus 1, and this guy, by shift operation, big O over 1 by shift operation, okay, and this is odd and even, okay, so this is addition by 1. So adding certain number, increasing by 1, typically there is separate CPU has separate operator in case of just one increment. This is I plus 1 means just it looks like I plus plus or I plus plus, okay. So this case can be done by big O of n. The reason is R equal R plus 1 is same to R plus plus in C language, okay. Okay, and R plus plus is one single operator. So calculated 1, okay. So here is 1, and it's same, but there's a minus. So in this case, total action time will be O of n, okay, for r minus y, okay. Because this is because r minus y takes of n when r and y are n bit integer. Okay. Okay, so it is division. Okay, so it takes big over n square, and it seems fine so far. There's no method look like, no method better, no better method for calculating division operation. Okay, and how about modular arithmetic? Before we start modular, then because modular operation is using division operation, because the modular operation usually takes the remainder was operation. Okay, so modular operation is x modulo n, that is described using this percent symbol here to be the remainder when x is divided by n. Okay, and that is used for primary testing and cryptography. Okay, and there is some condition like equivalent condition, that is x and y are congruent modulo n. Okay, so x and y is equivalent over modulo n means x and y has the same remainder when it divided by n, number n. Okay, so that this guy means when both x and y have same remainder of n, okay, then we say then x and y are equivalent over n. Okay, so that is equivalent. Okay, so it is same like this, and but typically the remainder is positive integer, or 0 or positive integer, but it's a natural number and 0. Okay, so that's equivalent in when we thinking about remainder. Okay, but in this case we have to consider minus value. Okay, so there's no reason to excluding minus value. Okay, so that is okay. So thing is like this: if 253, both two numbers, you have two numbers 13, and if you divide these two numbers by 16, but the remainder will be 13. Okay, so they are same remainder when you dividing 16, so that is same class. In other words, that is equivalent, okay, over the modulo 16. And in this case, this is minus 1. It's like it's not intuitive. When you divide something, you have a remainder, then the remainder value is minus 1. It's not that familiar thing, but say no way, no problem. Okay, you can take minus value. Okay, but so in this case still, yeah, it's equivalent 59 and minus 1 equivalent. Okay, over the modulo 16. Okay, so and you have modular operation. There's some rule like called substitution rule. So if x and x prime is equivalent, and y and y prime is equivalent over the same number in n, okay, then x plus y equal not equal is equivalent to x prime plus y plus y plus y prime x prime plus y prime over modulo n, and x times y is equivalent to the class of x prime times y prime over modulo n. Okay, so that is substitution rule, and this rule can be easily obtained by just calculating or giving some very simple example. Okay, so here is substitution rule. So I'm giving some example like this. example like here, okay? If 5 and maybe 12, 15 mod 10, okay? And it's the same, okay? It's the same. The value will be 5, okay? And maybe 2 mod 10 and 12 mod 10, okay? That is 2, okay? It's the same. Then when we think about 5 times 2 mod 10 and 15 times 12 mod 10, both the same value, 0, okay? So this is substitution rule, okay? And maybe this can be easily proved like this, okay? The number A can be written like A prime times N plus A double prime, okay? B equal A B prime can be written like this, N plus B double prime, okay? When you have this value, then definitely A times B equal A times B times, okay, N square plus A B times N plus A B times N okay, plus A B like here, okay. So if you divide this guy, then maybe this guy by n, then this can be 1, okay? This can be 0, the remainder, okay? Remainder value will be 0. This guy will be remainder will be 0, 0. So there's a mistake here. So total final result will be like this: A double prime and B double prime. And A double prime is the remainder of A, and when this A is divided by n, okay, B double prime is n, okay. So the remainder of B divided by n, okay, both are number remainder, okay. So the substitution rule will be fine, okay. So by using substitution rule, we can calculate some kind of operation like this exponential operation like here, 2 to the power of 345. Okay, but this calculation takes a long time because in this case we have to multiply number 2 by 345 times of multiplication operation. So it takes very long operation. But if this number is kind of modular operation, then the total operation time get very simple, okay? Because this guy and this guy and this guy is same number over the modular 31, okay? So when we calculate the modular operation over some kind of exponential number, then you can find a simplified method for calculating some kind of exponential number like here. So for example, 345 is equivalent to 2 to the power of 5 times 69, okay? That is equivalent to over 32 to the power of 69. and 32 is modulo 32 is 1 over modulo 31. So it can be simplified like here. The final value will be 1, like here. That is substitution rule. Okay. So that is how to add and multiply modulo operation. Typically, modulo operation is using division and its remainder. So by some kind of this method will be fine for addition and multiplication of a modulo operation here. Okay, and then the thing is how to compute this guy and that guy. It's a very simple way is just using several multiplication. Okay, y times of multiplication, and once you have final result, then maybe you can divide by n, then you can find the solution for this. Okay, but the problem is this guy takes very long time, and sometimes it will make some kind of overflow because x times y will be very big number. Okay, so this guy, okay, you can compute x times y mod n, okay, by multiplying x y times, and you can the result divide the result multiply y times first. You can divide the result by n. Okay, you can get answer by dividing the result by n. Okay, so you can compute this guy, but the problem is multiply takes long time. Okay, as many too many as that involves too many multiplication, and the result there and there are paths of overflow. That is the result for multiplication will be too big number. Okay, that cannot be handled normally in the computer. Okay, so that is it. So so like this, first intuitively to obtain this value, you just multiply x several times, n times. Okay, and once you have result of the multiplication, you will have now then you divide this number by n, then finally you can compute x times y mod n. Okay, but in this case there's a problem. First problem is just multiplying again takes too long time. Okay, especially when y is very big number. And second problem is if you get some value of multiplying same value, then the final result will be very huge number. This number is typically cannot be handled by certain simple computer system. So this value cannot be computed. So we have to think about the efficient way calculate for modular exponential problem. Okay. So here is the example. We need to calculate this value. Okay, this value can be written like this, and as you can see here, that will be very huge number. Okay, look at this. This is 2 to the power of 16, 19 times 19 times 5, 24 to 88. Okay, this is very huge number, and just the space to store this result will take how many bits? Okay, just 19 times 5 524 288. It is a kind of very huge number. Okay, so this too big, so it this cannot be handled in typical normal integer operation, integer addition, or storing the value. Normal typical integer system cannot handle this problem. So we need to design the simplified method. Okay, so this is phasing method. We can do better by starting with x and scaling repeatedly modulo n. And look at this. Okay, x. Once we have x, guess the value of x square mod n. Okay, and then maybe the resulting value will be 0, greater than 0 and less than n, and then scale again until you reach final result here. Okay, and in this case, total operation will be y times log y times. Okay, total multiplication operation will be log y times. Okay, and when y is this number. Okay, so also because you operate the modular operator every time you multiply, so the resulting value will be, the size will be less than n. Okay, so you can solve the problem together by using this method. Okay, so for example here, okay, for example here, look at this. Okay, this value is first time 2. Okay, mod 2 mod, for example 11, and then 2 square mod 11 equal 4. Okay, I'm sorry, it's too long, so I have to use some memo here. Okay, so this method is like this. When we compute 2 to the power of 100, for example, like here, okay, 1 to the power of 128, okay, mod 11, for example, okay, then the method is like this. First compute 2 okay, 2, okay, first calculate 2 mod 11 is 2, okay, then 2 to power 2 mod 11 equals 4. The next step is 2 to the 4 then equal 2 to 11. Okay, then mod, okay, equal 16 mod 11. Okay, equal 5. Okay, and 2 to the 8 mod 11 equal 5 equal 4. Okay, so you can compute potential by using substitution rule. Okay, rule. Okay, okay, and then it will simplify the computation. Okay, and until your computation finished until 2 to the power of 128. Okay, mod 11 will be 2 to the power of 64 mod 11 times okay, so mod 11. Okay, so you can calculate easily like this. Okay, then total in the case total number is log, okay, 1 to 8 plus 1. Okay, so rather than in this case, think about in typical multiplication, you have to multiply y times, that's the 128 times. Okay, but in this case, you don't have to, the number of multiplication is simplified. It is just a 6 times or 7 times something. Okay, 6 or 7 times. That is very hugely shorten the total execution time. Okay, total number of multiplication. Also, the result is the resulting value will be ranged from 0 to n minus 1, because the modular operator only takes remainder. Okay, so there's no bigger number than the n modular number. Okay, so total resulting number is small enough for calculating, useful in typical computer system. Okay, so anyway, that is this way. Okay, so this way is the modular operation. Okay, so if you think about 28, then maybe you have to compute like this. Okay, to 35. In this case, you only need to calculate this guy modulo n. Okay, so just by doubling, not doubling, squaring, and then takes the the appropriate number here, then we find obtain x to the power of 25. Okay, so and this algorithm can be written like this, recursively like this: x to the power of y equal x by, if y even, then written like this, y other than written like this, and there must have some kind of makeup here. Okay, and this guy can be written in like this way from this algorithm, this mathematical expression. So here, two ending number x to the power of y. Okay, here, and then there's the y by 2. Okay, and this can be done by shift operation, and even x square, the g square is needed some kind of multiplication operation, and modular operation takes division operation. So total action time of this guy will be here will be big O of n square. Okay, and this guy will be same here, n square here. Okay, and then this guy will be this guy is n minus 1. Okay, this guy takes Tn, and by using recursive relation, okay, you can calculate easily like here. So total execution time is big O of n to the 3. Okay, fine. Okay, this is the end of today's class, and happy holiday, not holiday, the national holiday, and take it easy, and see you next week. Okay, bye bye. Okay.